Hi, Julian here from PopcornFX. Today we are going to see how to project particles on the edges of a mesh. So usually when you use the projection node in PopcornFX, it will project on the surface of the mesh, not on the edges. And before 2.7, version 2.7, you had to, if you wanted to do this, you had to do it by hand. Now in 2.7 it's built in the projection node. You just have to check project on edges and it will simply work. So first I'm going to show you how to create the projection effect from scratch, and then I'll switch back to 2.6.4 of Popcorn to show you how to do it manually. And even though it's not needed in 2.7, this was originally asked by a client who is on 2.6, but I figured it would be useful for everyone to see how you can do that by hand and how the new projection node actually works in 2.7, because the projection node is a graph and it's actually doing the actual logic of projecting on edges with graph nodes. It's not a C++ built-in thing. So I'm going to go through all that process and explain all the details so you can understand the principles of when you have a point on the surface of a mesh, how to snap it to the closest edge. So first I am going to create a new effect from scratch and name that test proj. I'll create a multiply node, infinite, that spawns, let's say, 10,000 particles per second. I'll create a layer with a billboard node, hit Control R to restart. Now we have this thing running. So I have my particles all at the origin. So to start, I will spawn them on a shape, and then I will add a local to world node to make sure they're all in world space. Maybe that's too many particles. Just make it 1,000. Right, now if I add a physics node with an upward wind and some drag. So yeah, I'm in a Z-up project. So up is in the Z coordinate. It's not the default coordinate system if you create a new project from scratch with the default values, but here I'm in Z-up. So now I have my particles moving up, and if I want to project them on a shape, I just use the projection node, and here in the projection node I will need to wire the velocity as well, and I need here to wire a shape. So I'll just drop a shape node. By default, shape nodes use the sphere shape. And so now you can see that every frame the particles get reprojected on this shape, and the physics node still moves them upwards. So here I can add a vector field to have a more interesting movement. I'll make that animated a bit stronger maybe. Yeah. I'll make the particles smaller and I will add more particles so we see the motion better. Right. Perhaps that's too strong now. Yeah, anyway. So here I have my projection working. So that's on the sphere. If I want a mesh, I'll just change the shape type to mesh I will pick a mesh, and this mesh is pretty massive, so I will change the scale to something more reasonable. And now I have my particles that are projected on the mesh every frame, so they stay on the mesh surface. I'll quickly tweak the spawn shape. Let's say 0.8, and I'll make them live longer, say 3 seconds or 2 seconds. Right, so that's the basic rig for projecting on a mesh. I can move my spawn shape, and you will see that they keep projecting on the right place. So a little detail here. If I move the effect, you will see that even though I'm moving the position the effect is spawning on, the particles keep being projected at the origin, at the world origin. So here in the projection node I can check Localspace, and whenever I check Localspace it will basically move this shape to wherever the current effect is. So if I spawn multiple instances, each one will have that shape moved to wherever it is in the world. But there is one last detail. When I move the actual effect instance, because it projects the world space position of the previous frame, it will give that kind of weird wiggling effect as I move the shape around. So to fix this, there is one last thing I need to do, is to add a Localspace node on the position, and this Localspace node will every frame move the particle position to wherever the particle is, the effect is this frame, and it will offset basically every particle by the move offset of the effect every frame. So when the effect doesn't move, it doesn't do anything, but if I translate the effect 1 unit on X in one frame, this Localspace node will also translate all the particles from this effect instance by 1 unit left. So now when I move my instance, there are no more artifacts. So that's the basic setup. And if I want to project on the edges in 2.7, you just check the project on edges checkbox, and it magically works. So now I will show you how to do it the 2.6 way, or before 2.7. Going to 2.6 now. So new empty effect. I'm going to fast forward that so you don't have to sit through the same thing again. Right, so now I'm back to the same basic rig I had in 2.7, except you can see here that in 2.6 there are lots of artifacts. The reason for that is a small change we made in the 2.7 projection node that you had to do by hand in earlier versions. So before 2.7, the projection node will not store the projected position for the next frame. So this is why you see here that yellow line. The yellow line basically shows the where the value is stored and loaded the next frame. So this is what we call a discretization path. It's a pretty weird concept to wrap your head around if you're not familiar with it. I'll do a separated video for that, because it's pretty important. Once you get into advanced effects, it's pretty important to understand that concept. It's basically the way to do loads and stores between frames without explicit storage, because as you have noticed, the PopcornFX graph in version 2 doesn't have explicit storages, unlike version 1 and unlike other VFX systems such as Niagara or VFX graph. So to make this work without an explicit storage, we have that concept of a load store path that we call discretization path. So here basically the Localspace node uses a discretization node, which you can see as a store node, and you can see the path that the data takes once it gets reloaded on the next frame. So here this store node, if you walk back the yellow line all the way back up to the first spawn value, at the junction between spawn and evolve, that's where the data will be loaded. You don't actually need a discretization node here. It's just the transition between spawn and evolve that defines where this will be loaded. So basically here, these are the loads. The loads happen here. And if you take the position and walk all the way into the local space, this is where it gets stored. You see the yellow line doesn't continue after that. So here, that value is stored here, and on the next frame, it will get reloaded back there, and it will flow again through all those nodes. So the problem here is that the position that's stored at the end of a frame and reloaded on the next frame is not the projected position at all. It's actually just this position here. So the projection here behaves as an instant projection. Every frame, it takes these world space positions and tries to find the closest point on the mesh from those projections, and that's where you see artifacts, because the projection, the algorithm we use for projection is actually an approximation whose quality degrades as you get further and further away from the mesh. It's not an exact projection. So the quality is good when you're close to the surface, but degrades as you get further away. So obviously the imprecisions and errors accumulate using this way of doing things here as time goes by and as particles get further and further away from the mesh. So here we can visualize that pretty well if I just bring down the number of particles. And here with those two positions, I can very easily do a draw a line to display the projection vector between where the particles actually are and the projected position going out of the projection node. So to work around that, before 2.7, as I said, 2.7 now embeds those store nodes inside the projection node, so you don't have to worry about that anymore. But before 2.7, to make this work, you actually had to manually add those store nodes in here. So now you can see that it's much better. There are still some small artifacts, and that's because we don't store the reprojected velocity. So we need to do the same thing for the velocity here. And now everything is much smoother and looking the way we expect it to look. So yeah, as I was saying, here you can walk that back to understand what's happening. So here we have that store node. It goes back into the projection, walks all the way back up, goes back to the position pin, goes into local space, all the way up there, back to the physics, etc., up to the way it gets loaded on the next frame. Anyway, so that's the 2.6 setup. So now in 2.6, as I was saying before, you have that local space checkbox like 2.7, but there is no project on edge checkbox. So we are going to see how to do that by hand. So first thing, I am going to clean this up a bit and create a new local template. Just going to group those nodes and name that project on edge, just to make it more 2.7 like. I'll also reorder the shape input because I don't like where it is. Prefer to have it at the end. Right. So now I have that project on edge node, and now I can work entirely inside here. So you might have noticed that the projection node outputs a parametric coordinate value. So this gives you the parametric coordinates on the mesh where the final projected point is. So this means that you can do a shape sample and what's happening? Right, don't know why it wired that here. So that you can do a shape sample, and in the inputs of the shape sample you have that parametric coordinates. You can also hit Control T to toggle everything. And here, if I wire in the parametric coordinates that are output from the projection, here I resample the mesh at this location, and if I wire the position back in there, so here it explodes because it messes up the discretization paths. But if I use an assign node, that's what the assign node is for, is so you can keep the load and store paths going the way you want. So if I reassign this in here, this will give me the correct position back. So now the interesting thing, you're going to say what's the point of resampling the mesh at the same parametric coordinates to get the same position, because these positions are actually exactly the same as those here. Well, the thing is that I can now modify those parametric coordinates, and this is the place where we will change the parametric coordinates to project them on the closest edge of the current triangle. So when the shape is a mesh, the parametric coordinates store internally the ID of the triangle and the barycentric coordinates, the UV barycentric coordinates. So I want to keep the triangle ID the same, but to change the barycentric coordinates so that they get projected on the closest edge. So I'm going to show that in a minute. Here I will make another subgraph just to keep things readable and tidy. So here I just created two pass-through nodes, and I will Control G these and name that project PCoords on edge. So that's my new subgraph. I will quickly make this a bit more readable. Right. So now I have that template that takes the original projected on the surface parametric coordinates and outputs currently the same parametric coordinates, but will output the snapped on closest edge parametric coordinates. So in 2.7 you have a helper node that allows you to cleanly extract the information from the parametric coordinates. I'm quickly going to show that. But in 2.6 you have to do it by hand, unfortunately. Yeah, so here if I take some parametric coordinates, I have the disassemble parametric coordinates node into 7. So here you give it the parametric coordinates, it gives you the face ID, so that's the triangle ID, and the barycentric UV coordinates. And on that node, so that was actually the face ID and face UV of the box shape. So on that node you have a drop down where you can pick the shape type. If I pick mesh, I have triangle ID and barycentric UV coordinates. Back to 2.6 where you don't have that handy template and where we need to extract things by hand. So this is something you shouldn't do. That's why we added the template in 2.7, because the parametric coordinates are an opaque structure that we can change based on implementation, and in future versions we might change the way the bits are arranged in them. So you should avoid doing this. But before 2.7 you had no choice, and it just happens that the parametric coordinates for the meshes are the easiest ones to unpack. So I'll show how to do that. So you just drop a split vector 3 node. Here we will wire that into a construct vector 3 node. I'll wire everything back in. Right, so this is acting as a simple pass-through. So this is the triangle ID. And these two are the barycentric U and V chords. Right. So these are integers, and the barycentric coordinates are floats. So these are actually encoded, reinterpreted as integers. So to get them back as floats, I will use a construct vector 2D just to get back the 2D vector. I will do a as float node, which gives me back a float 2. So here this constructs an int2, this gives me a float 2. And just to get the pass-through thing going so I can check that everything works in the viewport, I will then re-switch that to integers, resplit it, rewire it in there, and as you can see, everything still works. But now I have my float2 vector, which are the barycentric coordinates. So from here in there, I will need to do something to project those UV barycentric coordinates to the closest edge. So to do that, first a quick explanation on barycentric coordinates. So if this is so let's say this is 0, this is 1, 1, this is my U axis, and this is my V axis. So if I plot the barycentric coordinates of a triangle, they will always fall in that area here. Anything outside that 0, 1 triangle in barycentric coordinates will be outside the physical triangle, no matter the size or the look of your actual triangle. Even if it's something, let's say like this, you will always have this mapped to 0, 1 in barycentric coordinates. That's what's great about barycentric coordinates, is that it's a much simpler representation of a generic triangle that doesn't take into account the shape of the triangle, and we do not care to project it on the closest edge. So here in that triangle, let's say the center should be somewhere around here. So when I have particles in there, in that area, I will want to project them on that edge here. Whenever I have particles in that area, I want to project them here, and same for that one, I want to project them here. And if we look in the barycentric coordinate space, this is exactly what it will do. If I can just get it to work, yeah. So everything in that area will get projected on that edge, everything in that area will get projected on that edge, etc. So to find when we have a point in the triangle and we have its barycentric coordinates, let's say somewhere here, to find inside which of those three areas the point lies, and therefore on which edge we should project it, it's actually pretty simple. So I'll switch to that graph view to show you the areas. So if I say, yeah, so that's just to display that line, to visualize the triangle. So here, if I do x greater than y, you can see that area, and this is actually the first line that we need, this line here, to define one of those three areas. So if I do if I do like 1 minus x greater than y, I get this one. And to get that line here, I'll just multiply that by 0.5. So this gives me this area. And you can see that when the barycentric coordinates of the point satisfy both this condition and this condition, it will mean that the point is inside that subtriangle here, so that we should project on that edge. And finally, for the last one, we simply have to flip, whoops, x and y, and this gives us the last one. Now to get the other side, that's just a matter of flipping the sign of the comparison. So with those three conditions, we can easily detect if a point is inside one of those three areas. So we are going to do that just now. So to do that, it will be much easier to use a script node rather than trying to do everything using nodes. So in this script node, so value, I rename that to UV, and I will make it have an output, let's say, is it inside? So I'll name that, let's say, no, actually, should project. And I name that proj on edge 0. So it should project, to project on that edge, it should project if this condition is true and if that condition is true, so x greater than y and half 1 minus x greater than y. So I'll just write that. So if uv.x is greater than y and 0.5 times uv.x is greater than y, uv.y, sorry. So if this is true, we are in that bottom area. And that's it. So I'll quickly copy paste that for the 3 edges. You'll see that I don't actually need the last one, but I'll do it for the sake of the example anyway. So for the second edge, it's actually very similar. So here we just have to flip the condition of both. That one, right. So it's when this condition is true and this condition is true, we are projecting on edge 1 here. So I'll just flip this. Flip that one. No, greater. Right, so that's project on edge 1, and the project on edge 2. Same principle. It's when this and this is true, then I project on edge 2. So 1 minus 6 lower than y. Oh, and this is totally wrong. I typed 1 times x. So lower than y and 1 minus y lower than x. Right? And I'll have to... when you have the little star here, it means that the script is modified but not applied. So if you go back in the graph and reopen a different node or script, it will lose your changes. So make sure to hit either Control S or Control Enter to make sure it gets applied properly. So this is 1 minus. And this is also 1 minus. Right. So now I have my 3 conditions that tell me whether or not I should project on each of those edges. So I'll actually change that script to also output the projected UV. So I'll name that proj UV. Here I'll simply do a simple pass-through just to make sure things are working, well, are not broken at least. Right, and now I'm going to wire in the logic of selecting each of those proj UV outputs based on the should project conditions, even though currently I'm just passing them through from the input UV without modification, but if everything goes right, we should see the same result here. So if we should project on edge 0, we will take that value, the projected value on edge 0. Otherwise, if we should project on edge 1, we will take the value projected on edge 1. And otherwise, it necessarily means if we're in neither of those two areas, if we're neither here nor here, it necessarily means we're there, because remember, as I was saying, the barycentric coordinates outside this region are invalid. So if we're not here, or if we're not, if we're not here, it means we're in there. So that's why I was saying we don't actually need that logic, because here we're not wiring this anywhere. So we're just taking, if this is false, we're just taking that last projected value, and we get this back in there to construct the final parametric coordinates. Right. So that's the main logic, and the only thing that's left is to actually project the particles on the edge. So we're going to do that right now. So this can be a bit tricky to explain visually, but basically to project a point in there on this edge, it will be 0 on y, obviously, because that edge is y equals 0. And the x value that we need to put in there is the previous x value divided by 1 minus the y value. So this is because we don't actually project straight down like this. What we want to do is to actually project along those lines like this, hence the division by 1 minus y. Same thing for that one. That edge is x equals 0, and y is y divided by 1 minus x to have that same projection pattern. Whoops. And the last one is actually a bit trickier, because we want to project along that way. And to do that, it's the x and y divided by x plus y. So we'll do just that. So to project on edge 0, we will reconstruct a float 2, setting 0 on y and dividing x by 1 minus y. And the problem here will be when y equals 1, if there is a point exactly on that edge up there, it will divide by 0, and this will produce garbage in the parametric coordinates. So we could work around that by using a saturate. I guess that would work, except it would project on x equals 1 instead of projecting it into x equals 0 as it should. So it doesn't matter that much. So you can use a saturate, or you can simply select, or using an inline if. So you can do if uv.y is greater or equal to a value close to 1, then you set it to 0, otherwise you set it to whatever the division does. Right, so when I validate the script, you can see that we have a partial projection on only the first edge of the triangles. So now we simply need to do the exact same thing for the other 3. So here it's 0 on u, on the u coordinate, and the v coordinate, it will be the same thing but flipped around. We divide y by 1 minus x, like so. And the last one is slightly different, and we can get rid of the select, because as we're going to divide u by that, oh, actually, we might need a select in case the barycentric coordinate is exactly at 0. It will do 0 divided by 0. Yeah, that's a bad idea. So yeah, I'll add the if as well here. So if d is greater than very small value, then it's safe to divide. Otherwise, we just return 0. And that's it. We're now projecting on all the three edges, and we shouldn't have any particle left that's not on an edge. Yep, look good. So small detail here, if this template project on edge is given a shape that's not a mesh, it will totally mess up things. So let's say I wire in the sphere. As you can see, everything is messed up. That's because the parametric coordinates of a sphere are absolutely not stored with a triangle ID and barycentric coordinates. There's no such thing as a triangle ID in the sphere shape. If you wire in another shape, let's say a box, you'll get kind of something projected on the box, but still going totally bonkers. So to work around that, what we can do to allow you to plug shapes that aren't meshes in that template and not have everything break, we can do a test on the type of shape. So in here, project on edge, we can, well, no, not here actually, we can take the shape, take a shape properties and expose the shape type. I'll wire that into a script because in 2.6 you don't have any other way to do that. In 2.7 you have a node that tests if a shape is a certain type and just outputs a Boolean value, true or false. But in 2.6 you have to do it by hand. So here I'll simply write if shape type equals shape type dot mesh, then it's a mesh. And if it's not a mesh, it will be false. If it's a mesh, it will be true. And now I can very easily do an if it's a mesh, then I output this. And if it's not a mesh, I output the original parametric coordinates, then give that back to the shape sample. So whenever it's not a mesh, it will entirely discard the result of this project on parametric coordinate on edge logic, and it will just use the original parametric coordinates. So now if I go back in here and wire in my shape, I have the proper behavior of the particles projected on the shape without artifacts. So that's it for this video. I hope you liked it. If you did, give it a thumbs up and don't hesitate to comment if you have any questions. See you next time.